For our last topic, we're going to talk about real numbers. Now that's a pretty broad topic, so let's focus in on why we're talking about real numbers. As we've gone through this course, we've really developed the number system. We've started by talking about counting numbers, and then we added 0 to that set of counting numbers to create the set of whole numbers. When we also included the opposites of all those numbers, we had the integers. And when we looked at some of the numbers in between those integers that were created by writing fractions, we had what were called the rational numbers. Now, if you look at this set of numbers that we've looked at so far, you can see that they cover a lot of the numbers that we use in everyday life. But there's another set of numbers that describe numbers that exist in the real world, and those are irrational numbers. Irrational numbers are non-repeating, non-terminating decimal numbers, although when we look at an irrational number, it may not look like a decimal number. Some examples of irrational numbers are numbers like pi. Now we know that pi has a decimal approximation of 3.14, but pi actually is a decimal number that, as a decimal, never repeats and never terminates. Square root of 2 is also an irrational number. We can't write the square root of 2 as a fraction. We could write it as a non-repeating, non-terminating decimal approximation, but both pi and the square root of 2 cannot be written as fractions. So the big distinction between rational numbers and irrational numbers is that rational numbers are numbers that can be written as fractions, and irrational numbers are numbers that cannot be written as fractions. However, they're all considered real numbers. The cube root of 10 is another example of an irrational number. And this decimal number would be an irrational number because even though we do see a pattern in the digits, the pattern is not one that allows blocks of digits to repeat, so it would be considered a non-repeating, non-terminating decimal. So it is irrational. So when we're looking at a number that exists in the real world, a number that's a real number, we can decide which of these sets that number belongs to, and it may belong to more than one of the sets. For example, think about the number -7. -7 is not a counting number, and it's not a whole number, but it is an integer, and it is rational because it could be written as a fraction. We could write it as -7/1. But it's not irrational. So it belongs to the set of integers and the set of rational numbers. And because integers and rational numbers are real numbers, then it also belongs to that set. How about 14/3? Well, 14/3 is not a counting number, it's not a whole number, it's not an integer, but it is a rational number. And if a number is rational, it will not be irrational. And all of these numbers are real numbers. So now that we have this set of numbers that we call irrational numbers, we can start to look at some specific numbers that are part of that set. Numbers like square roots. Now let's think about what a square root means. If we ask what are the square roots of 36, we're asking what numbers can we square to get 36? Well, 6 is a pretty obvious one. 6 is the square root of 36 because 6 squared is 36. But this one may not be quite so obvious. -6 is also a square root of 36 because if we take -6 times itself, we still get 36. So what we've seen just illustrates that every positive number has two square roots. 36 has a positive square root of 6 and a negative square root of -6. The positive square root is called the principal square root. Now, suppose we're asked to find the square roots of 25. Well, we're being asked what numbers do we square to get 25, and there are two of those numbers, 5 and -5. If we're asked to find the principal square root of 25, then we're being asked for that positive number that we can square to get 25, and that is just the positive 5. Now, if we're asked to find a square root symbolically, in this case, the square root of 25 using this radical sign, then in that symbolism we're being told which of those two square roots of 25 we're looking for. In this case, we're looking for the positive square root. But if this is what we see symbolically, the negative sign in front of that radical means we're looking for the negative square root of 25. Now, real numbers are numbers that exist in the real world. They're numbers that we could use to measure something, or there's some numbers that we could put on a number line. So since we could actually measure with these numbers, we could ask the question, well, how long would this number be if we used it to measure something? So let's look at that. How long is the square root of 2? So here's how we're going to explore that. We know there's this relationship between squares and square roots. And we're going to think about squares that are positioned on dot paper. So on this dot paper, each dot is 1 unit apart from the next dot in the same row or the same column. So if we look at this square, we can see that the length of the side of the square is 1. And we can see that the area of the square is 1 square unit. If we look at this square, we can see that the length of its side is 2, and the area, the number of squares inside this square, the number of square units inside the square, is 4. This square has a side length of 3. And inside the square, we can see 9 square units. So how can we use this to find out how long the square root of 2 is? Well, think about these squares. We can measure how long 1 is, or 2 is, or 3 is by looking at the length of the side of the square. And we can get to those numbers, 1, 2, and 3, by taking the square root of the area of the square. So if we can just find a square that has an area of 2, then we know that the length of the side of the square will be the square root of 2. Well, take a look at that square. The area of the square is 2 square units. And you can probably see that a little more clearly if you think about dividing the inside of the square up into these little triangles. If you put the triangles together, you have 2 square units. So that means that the length of the side of the square that has an area of 2 square units would have to be the square root of 2. So that distance right there would be the square root of 2 units. Now another thing we can see from this is exactly where the square root of 2 would be located between these whole numbers that we have. The square root of 2 has to be between 1 and 2 because 2 is between 1 and 4. The area of 2 is between the area of 1 and the area of 4, so the side length, that's the square root of 2, is between a side length of 1 and a side length of 2. Now when we're looking at roots, when we're looking at square roots or cube roots or any kind of root, we can think about simplifying them. So for example, the square root of 1 is 1 because 1 squared is 1. And the square root of 4 is 2 because 2 squared is 4. The square root of 9 is 3 because 3 squared is 9. But how do we simplify something like the square root of 18? Well, 18 is not a perfect square, but if we think about the factors of 18, we can see that 18 does have a perfect square factor. 18 is 2 times 3 times 3, and because it has two factors of 3, and 3 squared is 9, that means 18 has a perfect square factor of 9. So we can simplify the square root of 18 by removing the square root of 9 from the square root of 18. Square root of 9 is 3, so we can rewrite the square root of 18 as 3 times the square root of 2. Now when we're trying to simplify a square root that does not have a perfect square underneath the radical, we're always going to be looking for perfect square factors inside that radicand. The radicand is the number underneath the radical sign. So if I think of 75 as being 3 times 5 times 5, I can see that 75 does have a perfect square factor. That's coming from the 5 times 5, which is 25. And since the square root of 25 is 5, the square root of 75 is 5 times the square root of 3. Now when we have cube roots, what we're looking for is a perfect cube underneath that radical sign. 8 is a perfect cube because it's 2 times 2 times 2. So the square or the cube root of 8 is 2. 24 is not a perfect cube, but it does have a perfect cube factor. 24 is 2 times 2 times 2 times 3, and those three factors of 2 make a perfect cube factor of 8. So the cube root of 24 is the same thing as the cube root of 8 times 3, which is 2 times the cube root of 3. Now since these numbers that we've just started looking at, these square roots and cube roots, since they're real numbers, they really do exist on the number line, which means they can be compared to any other number on the number line, and we can determine which of those numbers are smaller and which are larger. And because of that, we can order any number that's a real number from smallest to largest. So we're going to do that with these numbers. Now you may be thinking that you can't do this without a calculator, but you really can, because all we need to do is have a way to compare the numbers. We don't necessarily have to know their exact values. So if I start to look at these numbers, I can think of 8.9, 8 and 9/10 as being a number that I can pretty clearly understand. 8 and 9/10 is 8 and 9/10. I know what that means. 65%, I might want to think about what percent means. It means out of 100, so 65% means 65 hundredths. So even now I can tell that the 65% is much smaller than the 8 and 9/10. Now what do I do with the square root of 65? Well, let's just approximate it. 65 is not a perfect square. If it were, it would be easy to simplify this expression. So I'm going to think about a perfect square that's really close to 65, something like 64. So the square root of 65 is really close to the square root of 64, and I know that the square root of 64 is 8. So the square root of 65 would have to be just a little bit bigger than that 8. And for our purposes for comparing, that's good enough to just say that the square root of 65 is a little bit bigger than 8. And then 31/4, well, that's an improper fraction. I can certainly think of that as the mixed number 7 3/4 so that I can compare these numbers. So we were looking for the smallest number in this list, and I think it's pretty clear that 65 hundredths is the smallest number. The next smallest number after that would have to be the 7 3/4, because the next number after that would be the square root of 65. It's a little bit bigger than 8. That's got to be bigger than 7 3/4. And then finally, the 8 and 9/10 is a lot bigger than 8, so it has to be the largest number. So from smallest to largest, the numbers are 65%, 31/4, the square root of 65, and 8 9/10. So let's take a look at a problem that was given to 8th grade students on the MAP test. This is a DESE released item from the 8th grade MAP test. It says points A and B shown on the coordinate grid represent two vertices of a right triangle. A line drawn between points A and B forms the hypotenuse of the right triangle. What are two different sets of coordinates for point C that could complete the right triangle ABC? And then we're asked to find the length of that hypotenuse. So let's first of all take a look at the first part of this question that's asking us to visualize a right triangle that can be drawn with that line segment as being the hypotenuse. So here's one of the triangles they're talking about, and that triangle would have a vertex at the point 3, 1. And here is the second right triangle they're talking about. That one would have a vertex at -1, -2. So the first part of this question is fairly straightforward. Now the second part says to find the length of the hypotenuse. That's the length of that red line segment. And in order to do that, we have to remember the Pythagorean theorem, which relates the lengths of the sides of a right triangle. So if we have a right triangle, that right triangle has legs that we're going to call A and B. Now the legs are the sides of the right triangle that form the right angle. And it has a length of the third side, which we call the hypotenuse, that we're going to label C. And if we have labeled the legs of our right triangle A and B and the hypotenuse C, then the Pythagorean theorem says that A squared plus B squared will always equal C squared. Now we can use that to find a length of any side of a right triangle if we know the other two sides. So in this right triangle, we know the hypotenuse, we know one of the legs, but we don't know the length of the third leg. So we could say that x squared plus 4 squared equals 6 squared, which means that x squared would equal 20, and x would be the square root of 20, which we could simplify as 2 times the square root of 5. So we can find the length of any side of a right triangle if we know two of the other side's lengths. So let's go back to this question. The last part of it was to find the length of the hypotenuse in units and write your answer. So what we need to know to find the length of the hypotenuse, that red line segment, is how long are the other two sides. And we can see that this side, this blue side, measures 3 units long, and this side, the one that's purple, measures 4 units long. So we want to know the length of the hypotenuse, that value for x. And according to the Pythagorean theorem, 3 squared plus 4 squared has to equal x squared, which means x squared is 25 or x is 5. So the length of the hypotenuse is 5 units long. Here's one more sample item. This is a sample map item, once again for grade 8 from DESE. It says Jason needs to nail 2 diagonal boards onto a 5-foot by 6-foot gate for reinforcement. How long of a board will he need to buy to be able to cut both boards for the reinforcement? Now this one has a little bit of a trick to it, but let's start by figuring out what exactly they're talking about with these boards that he's going to be cutting. So if you look at the diagonals, what you're going to see is some right triangles, and we're going to concentrate on one of those right triangles that has a leg that measures 5 feet and another leg that measures 6 feet. The hypotenuse is that diagonal they're talking about, so we need to find the length of the diagonal. We'll call that x, and we'll use the Pythagorean theorem, which says 5 squared plus 6 squared would have to equal x squared. Now that means that x squared would have to equal 61, which means x is the square root of 61 feet. That's the length of one diagonal. But he needs to cut boards for both diagonals, and those diagonals are the same length, which means two of the diagonals, two of those x's, would be 2 times the square root of 61 feet. So the board that he has to buy would have to be at least 2 times the square root of feet long. So that's the end of our discussion of Pythagorean theorem, and real numbers. We'll do a little more practice in class.